Now see the example where we will be using Ampere circuit law to calculate magnetic field. Suppose you have got long conductor current carrying wire like this, whose cross section area is here circular, and it is carrying current I throughout here, whose radius is, suppose I have taken here A. So we have to calculate magnetic field at 2 points. First one is R is greater than A, R is any point outside which is greater than the radius, and second point R is less than A, that is inside. Suppose you want to calculate magnetic field at this point which is out of this current carrying conductor, cylindrical wire. So by taking this one, we draw an Amperian loop in this way, and we take again in the same manner here the B here and dl already, which we have used again and again, and then we can write here B dl is equal to here again B dl cos theta dot product theta 0. So we can write here B dl, and B dl according to Ampere circuit law will be here, that is a mu naught I, because this is the I is the total current enclosed by this loop. So mu naught I is equal to B into 2 pi r. So we will be getting B is equal to mu naught I upon 2 pi r. That means outside this conductor B is inversely proportional to R. So this is the outside we have calculated. We can also calculate similarly the inside. Inside the conductor, when we are going to calculate magnetic field, again we can use Ampere circuit law, but here we will take this point, suppose R is here, and we draw loop, this thing is here. So this point will be here R. In this case, when we will be integrating, so we can write in this case B dot dl is equal to mu naught I dash. I dash is the current passing through this cross section area which is enclosed by this Amperian loop. So we can also write here integration of this is here 2 pi r into B is equal to mu naught I dash. Now I dash we can calculate. We can calculate current per unit area, then we can calculate the current passing through this loop. So the current per unit area we can write here current per unit cross section area is equal to I upon pi a square. So current through the loop which we will be getting, so I dash is equal to I upon pi a square into pi r square. This pi and pi will get cancelled. So now we can replace this value over here. So we will be getting 2 pi r into B is equal to mu naught I r square upon a square. Now we can cancel this r and this r. So we will be getting B is equal to mu naught I r upon twice of pi a square. Here inside it we are getting B is proportional to r. But inside this there is a material also, because we have taken the solid conductor and material is throughout here. So in place of the mu we can write here mu r. So is the mu r we can replace here. This is called a relative permeability of the material. So here also we can introduce here, that is a mu r. So here is mu r, because that is inside the material. So we have to include the relative magnetic permeability of the material. So now we have seen the magnetic field in both the cases, inside and outside, and now we can draw the graph. Graphically also we can study how does this magnetic field vary. So suppose you have taken, this is a x axis and this is y axis, where we have taken B and R. So we will be getting magnetic field here, that is B is proportional to R, that is from center to the surface. At the surface magnetic field is maximum, after that it reduces, that is inversely proportional to this. So here B is inversely proportional to R. So this is the variation of the magnetic field with the distance.